Hello and welcome to Bay College's Intermediate Algebra online lectures. My name is Jim Helmer. Today we're going to take a look at sections 2.5 that deals with linear inequalities, and we're also going to look at how that applies to systems of linear inequalities, which is section 3.7. The first thing I'm going to draw to your attention is a linear equation. At this point in algebra, we should have worked with linear equations somewhat. We should have an understanding of that we could solve for either of these variables. Maybe we put it into slope-intercept form, essentially solve it for y. Whatever form we deal with it, like I said, we should be somewhat familiar with linear equations. Well, how linear equations differ than linear inequalities is just that. They are inequalities. This standard form of a linear inequality is less than, but it could be greater than, or less than or equal to, or greater than or equal to. Either of these symbols could be substituted into there. So what we do with these type of inequalities is we graph them, because with a linear equation we graph a line. With a linear inequality, excuse me, we're actually looking for an area that makes a true statement. So if we look at this linear inequality, we have y is greater than or equal to negative x plus 4. Now, how we graph a linear inequality isn't much different than how we graph a linear equation. We essentially want to graph it as just that, a linear equation, so we can think of this as an equal sign just for a moment. Let me grab a piece of chalk here. I'm going to graph this using the intercepts. For me, that's a nice, easy way to do it for this equation. We could use the intercept and then slope, or just pick 2 points and graph the line, whatever you choose to do. But I'm going to use the intercepts. When x is 0, y is greater than or equal to 4. Well, right now I'm not too worried about that. I'm just going to graph the value 0, 4 if this were an equal sign. And then I'm going to find the other intercept, my x-intercept. If this is 0, negative what plus 4 is 0? Well, 4 would make this a true statement equal to 0. Negative 4 plus 4. So the value of x would be 4. So now I have the two intercepts. Now, before I graph this line, because we have 2 points, we can now graph a line, I assess this inequality. It can be equal to, which means the values on the line can be true in this equation. So when that's the case, when we have an equal to symbol in there, we use a solid line. Now, had this been a less than or greater than without the equal to, we'd want to use a dash line, indicating that the values on this line do not make a true statement. So we want to just have our solid line. It's graphed now. Now where this becomes different, because on a line we're looking for the points on the line. In an inequality we're looking for the area. Well, if we just assess this for a moment, we actually split our Cartesian graph into two areas: the area above the line and the area below the line. Now, the best way that I feel to work with this, to find that area, is to choose a test point that is not on the line, either to the left of the line or to the right of the line or above the line or below the line. Wherever, just choose a test point. My go-to test point, if it's available and not on my line, is 0, 0. So this is what I'm going to test. I'm going to test 0, 0. And I essentially do that by putting it into this equation. I'm looking for, does this make it a true statement or does it make it a false statement? Well, if I put that in, 0 greater than or equal to minus 0 plus 4. And of course, through some simplification, negative 4 and 0 is just 4. Is 0 greater than or equal to 4? This is not true. Well, that tells me everything I need to know about this linear inequality. If this point lies to this side of the line is not true, then every point on the other side of the line must be true. So I can just shade this side of my graph. And whether you use arrows or you shade it in, I choose arrows because when we see in 3.7 we get to systems, you'll see how the arrows actually make it a little bit more efficient. Maybe in your textbooks or in other videos you see they use two different colors, and where those colors overlap, they get a new color. Well, chalk doesn't allow us to have that, so I use arrows. So that was not a true statement, so the other side of the line is true. So maybe what I want to do here is pick another test point just to be sure that makes a true statement. I'm not going to do that here for time's sake, but it's always good to check your work. All right, we're going to move on to another linear inequality. And hopefully, with our background on lines, we recall that if we had y equals to some number, we actually have a horizontal line. Well, we can graph this as a horizontal line, but we look at this and say, okay, if this is a horizontal line, it cannot be equal to, this is just y greater than -2. That tells me what type of line I'm going to draw. A solid line or a dashed line? Well, since it's just greater to and not equal to, we don't want to use a solid line. We're going to use a dashed line because it does not equal the values on there. Well, if this was y equals -2, we'd be right here at -2 when we draw our horizontal line. But since it's just y greater than -2, we use a dashed line. And that dashed line, again, indicates that it does not include the values on the line. So -2 is not part of the solution. Now I can pick a test point. Just like I did in the previous example, my 0, 0 is available. Well, I don't have an x in here because x doesn't matter. The domain is all real numbers for x. So x can be anything in this case. But we put in the other value of my test point 0, 0, and that would be y is 0. Is 0 greater than or equal, or excuse me, greater than -2? Yes, 0 is greater than -2, so this is true for this y value. So since it's true, we shade that side. If I choose a value over here, it's going to make a false statement. So any value over here will be true. And maybe if we're intuitive enough, we can look at this and say the y values are greater than -2. Well, anything above this gives me a y value greater than -2, so that's a true statement. Now the next one is x is less than or equal to 5. If we recall from our linear equations, x equals a number is a vertical line. And that vertical line is x is 5. Now, because this is equal to, we're going to draw this vertical line at x equal to 5 for all values of x, or all values of y, I should say. But we're going to use a solid line because x is less than or equal to 5. So the values on the line make a true statement. So we draw our vertical line at x equals 5. And now we pick a test point, just like we did in the last two examples. 0, 0 is available. I'm going to use it. Well, there is no y, so the 0 for the y I don't have to plug in. So I just plug in the 0 for the x. Is 0 less than or equal to 5? Yes, that's a true statement. 0 is less than 5. So we shade the side of the line in which our test point was true. So any x value over here is less than 5. And again, if we think about it, yeah, these numbers to the left are going to be less than 5. So this is the area for this vertical line. Now, these were simple examples. Hopefully it refreshed your memory on how we deal with these special lines, our horizontal and vertical line. But now we have one of our standard lines here. But now this is, again, an inequality. It's in standard form. 3x minus 2y is less than or equal to 12. So we want to find at least 2 points, or maybe we put this in the slope-intercept form. I'm going to use the intercepts myself. So if x is 0, -2 times what value would be 12? Well, that would be a -6. So that's this value right here. When x is 0, y is -6. And maybe I'm going to be asked to label my points. So I'm going to label 0, -6. Now, if y is 0, what times 3 would give me 12? 4. So this point here is 4, 0. So I labeled them, and I can see, OK, this is a line that increases from left to right. It must have a positive slope. So maybe if you did put it into slope-intercept form, you'd see it does have a positive slope of 3/2. So now we have this. We're ready to draw the line. But I'm going to make sure what type of line, a dashed line or a solid line. Since it does include, it could be equal to the points on the line, I'm going to use a solid line here. So there is my solid line. Now I want to pick a test point. I'm going to choose 0, 0. But if that wasn't available, maybe our line goes through the origin, I could pick any other point. I could choose 1, 1, or I could choose -1, -1, or any other value as long as it's not on my line. But I'm going to use 0, 0 because 0 is a real easy number to work with, whether I'm multiplying by it or adding by it, as long as I never divide by it, right? So I'm going to test 0, 0. 3 times 0 is 0. Minus 2 times 0 is 0. Is less than or equal to 12. Well, 0 minus 0 is 0. 0 is less than or equal to 12. So my test point here is a true statement. So I'm going to shade the side of the line that my test point made it true. And that's anything above this line. And we can see that's the shaded area. Any point that I choose in this area will make a true statement. So now that we have an understanding of how to graph inequalities, we're going to look at systems of inequalities. This is something that hopefully we've seen before with the system of linear equalities. Well, here we have inequalities. So we're going to look at it nice enough that this line is in slope-intercept form, so it's really easy to graph. And I say, you know what? I'm going to use a solid line because it could be equal to. So I look at this and say, OK, well, the y-intercept is a -3. So I graph the point 0, -3. And the x-intercept is going to be 3, 0. So when y is 0, x would be 3. 3 minus 3 is 0. So that's this value here. And again, I look at it and make sure what type of line, a solid line, because it could equal the values on the line. And we have that line. Now we look at this one. I think our instructors are trying to trick us because it almost looks like it's in slope-intercept. The order has just changed. So maybe you want to switch it around just so that you can look at it and say, you know what? I know that the intercept is -1 and the slope is -1. So maybe you want to switch it around, or maybe you're comfortable with that. Either one works. We're going to look at this and say, OK, well, the y-intercept is -1. And the x-intercept is also -1. One thing to check is we're going to see a decreasing slope. A slope of -1 tells me it's decreasing. Now, what kind of line? It could equal the values on the line because it's greater than or equal to. So we're going to go ahead and draw a solid line here. Now, here's my two lines. What I want to do here is I want to pick a test point. But before I go any further, I want to do a little bit of accounting. I want to keep track of what I'm doing here. This was the first equation. So I'm going to choose a test point and check it in that equation. So let's make sure we know which one's which. We don't want to confuse our lines. This was the second equation I graphed, so I'm going to put a 2 there and label this as equation 2. Now, the reason why I do this is because the test point I choose, I'm going to test in one, but I'm going to use that same test point and test it in the other. So I have to choose a point that is not on either of these lines. Well, my go-to value of 0, 0 is available, so I'm going to use that. And I'm going to test it in equation 1 first. 0 is greater than or equal to 0 minus 3. 0 is greater than 0 minus 3 is -3. Is 0 greater than or equal to -3? It is. So that's a true statement for this line. And I make sure it's this line. This is the one I just tested. And the point lies above this line in this example. So I'm going to draw my arrows from that line. Now, you'll see I use these arrows, again, because we don't have some of the other tools. Maybe I could use some colored chalk so we'd see the area. But my arrows are going this way for this line. Now I'm going to test that same test point in line number 2, the one I labeled as line number 2. So I'm going to put 0 in here, less than or equal to -1 minus 0. So I end up, when I simplify, to 0 is greater than or equal to -1. Is that a true statement? Well, yes, 0 is greater than any negative number. It lies to the right on our number line. So we know that this test point, 0, 0, is on this side of the line, and it made a true statement. So I'm going to draw my arrows that show the area for that line that are true. And the reason why I do the lines like this instead of the shading area is because then we can see like a waffle pattern, or we can see where the lines cross. And that is the area of shading. If you want to take it further, maybe make it more visible for your instructor, you can go ahead and actually shade it in a little darker, which is not exactly the easiest thing to do with chalk. But you can see any value in this area will make both statements true statements. And that is our goal of systems of linear inequalities, is we want to find the area on the graph that makes all the equations involved true statements. This has been Intermediate Algebra Lecture Series here at Bay College. I'm Jim Helmer. Thank you for watching.